Today we are going to learn about mastering PyTorch Tensor Indexing Techniques. We'll dive into efficient tensor indexing methods in PyTorch to enhance your data manipulation skills and optimize model performance. Welcome to our video on mastering PyTorch Tensor Indexing Techniques. Tensor indexing is a fundamental concept in PyTorch that allows you to access and modify elements within your data structures efficiently. This skill is crucial for manipulating datasets and optimizing the performance of your machine learning models. In today's video, we will cover a range of indexing methods from basic to advanced, equipping you with the skills needed to handle real-world datasets effectively. Whether you are a data scientist or a machine learning engineer, mastering these techniques will enhance your ability to work with large datasets and improve your model's performance. Let's embark on this journey to deepen our understanding of PyTorch tensor indexing. In this section, we'll start with the basics of tensor indexing in PyTorch. Tensor indexing refers to the way we access elements within a tensor using indices. It's similar to accessing elements in a list or an array in Python. You can use integers to access specific elements, colons for slicing, and even negative values to access elements from the end of a tensor. For example, tensor 0 would access the first element, while tensor -1 accesses the last one. Slicing, like tensor 1 to 4, allows you to access a range of elements. Understanding these basics is crucial as they form the foundation for more advanced indexing techniques. Let's see how these methods work in practice with some code examples. Moving on to more advanced techniques, slicing and dicing your tensors allows for more flexible data manipulation. With slicing, you can specify a step size, like in tensor 2, which accesses every second element. When dealing with multidimensional tensors, you can slice each dimension separately, such as tensor 1 to 3, for a 2D tensor, which accesses all rows but only the second and third columns. The ellipsis can be used to represent multiple dimensions, making your code cleaner and more readable. For instance, tensor 0 accesses the first element of the last dimension, regardless of how many dimensions preceded. By combining these techniques, you can extract complex subsets of data efficiently. These methods are particularly useful when working with large datasets or when preparing data for model input.
Boolean indexing is a powerful technique for selecting data based on specific conditions. This method involves creating a Boolean mask, which is essentially a tensor of the same shape as the one you're indexing, but filled with true or false values based on a condition. For example, if you have a tensor data and you want to select all elements greater than 5, you would create a mask like mask equals data greater than 5. Applying this mask to the original tensor with data mask returns a new tensor containing only the elements where the condition is true. This technique is incredibly useful for filtering data efficiently and can be applied to any condition, making it versatile for different datasets. Let's look at some examples to see Boolean indexing in action. The gather and scatter functions in PyTorch offer advanced ways to index tensors using other tensors. The gather function allows you to extract elements from a tensor based on indices provided by another tensor. This is particularly useful when you need to rearrange data according to specific patterns. Conversely, the scatter function enables you to distribute values from one tensor into another based on indices. This is useful for tasks like updating specific elements in a tensor efficiently. Both functions are essential for complex data manipulations and can greatly optimize your code when used correctly. We'll dive into some practical examples to illustrate how you can leverage these functions in your projects. Now that we've covered various indexing techniques, let's apply them to real-world datasets. Indexing is often used in data preprocessing to clean and prepare data for analysis or modeling. For example, you might use Boolean indexing to filter out missing or outlier data points. Additionally, advanced slicing can help you extract specific features from a dataset. These techniques not only make your data manipulation tasks more efficient but also improve the performance of your models by ensuring that only the relevant data is fed into them. In this segment, we'll explore how these methods can be applied to common datasets, highlighting the performance gains and practical benefits they offer.
While tensor indexing is a powerful tool, it's not without its challenges. One common pitfall is encountering out-of-bounds indices, which can lead to runtime errors. Ensuring that your indices are within the valid range of your tensor's dimensions is crucial. Another issue is incompatible shapes, especially when performing operations like gather and scatter, where the shape of the index tensor must align with the target tensor. Performance bottlenecks can also arise when using inefficient indexing methods on large datasets. To avoid these pitfalls, it's important to thoroughly test your indexing code and use debugging tools to identify and resolve issues quickly. This section will provide tips and strategies to help you avoid these common mistakes and ensure your code runs smoothly.
Indexing methods can have significant performance implications, especially when working with large datasets. Basic slicing is often more efficient than advanced techniques like gather and scatter, as it directly accesses memory without additional overhead. However, advanced methods offer flexibility that can sometimes justify their use despite higher computational costs. Understanding the performance trade-offs of different indexing techniques is key to optimizing your code. Profiling your code to identify bottlenecks and experimenting with different methods can lead to substantial performance improvements. By choosing the right indexing method for your specific use case, you can achieve a balance between efficiency and functionality, ensuring that your models run as optimally as possible. Maintaining readability and efficiency in your code is crucial, especially when working with complex indexing operations. Readable code is easier to debug, maintain, and collaborate on. Using meaningful variable names and documenting your indexing logic can greatly enhance the clarity of your code. While efficiency is important, it should not come at the expense of readability. Striking a balance between the two often involves refactoring complex indexing operations into simpler, well-documented steps. This approach not only makes your code more understandable but also reduces the likelihood of errors. By following best practices, you can ensure that your code remains both efficient and accessible to others.
As we wrap up, let's recap what we've learned today. We've explored a variety of tensor indexing techniques in PyTorch, from basic to advanced, each with its own applications and benefits. Mastering these methods is crucial for efficient data manipulation and can significantly enhance the performance of your machine learning models. We've also discussed the importance of avoiding common pitfalls and maintaining readability and efficiency in your code. Remember, the key to mastering these techniques is continued practice and experimentation. We hope this video has provided you with valuable insights and tools to take your PyTorch skills to the next level. Thank you for watching, and happy coding!